Okay, now let's look at the following situation. Let's say you have a group G star and you have a normal subgroup of it, H star, H different than the empty set. Then the following interesting condition will hold. If you take G star H star, the inverse of G, that will belong to the set of the subgroup H for all elements in the set G of the group G. So here is the hypothesis. So let G star be a group and let H star be a normal subgroup of G star, and H is not empty with H different than the empty set. Then we get this property. G star H star G inverse is an element of H for all elements G in the group and all elements H in the subgroup. Okay, so here's a proof of this. So let's start with G in group G, H in subgroup H. We want to show that this expression belongs in H. Now, let's pinpoint to the fact that H is a normal subgroup. So there are two things that you will get, or there is one thing that you're going to get from definition, is that the left coset generated by H, the left coset generated by G in G, so the left coset of H generated by G is identical to the right coset generated by G. That's our definition of a H being a normal subgroup. So let's talk about G star lower h. G star lower h is an element of the left coset G star upper h. But since the left coset generated by G is equal to the right coset generated by G, then G star lower h also belongs to the right coset. H star, upper H star G. Now, but when you belong to the right coset, then you have the following format: an element of H star G. So this leads to the following equality, that G star lower H, G star lower H has to equal to some H1 star G, where H1 is in upper H. Now use a property of algebra. Since G is a group element, you can multiply from the right from its inverse. Its inverse exists. So multiply from the right by the inverse. Multiply from the right by the inverse. So we get G star H equals to H1 star G. So multiply from the right by G inverse, and as you can see on the right hand side, the G's cancel. And on the left hand side, you get what you're after. So those cancel, that becomes the identity. So you get G star lower h star the inverse of G equals H1, which we know belongs in H. So our proof is complete. Now, the converse holds as well. The converse being, if you have a subgroup H where this condition is satisfied, G star H star the inverse for all G and H, then the group will have to be, the subgroup will have to be normal. So let's write that converse and see why it also holds. So the converse holds as well. Now, what's the converse? So let me see if I can fix my marker here. One moment. So let G star be a group. Let G star be a group, and let H star be a subgroup of G star with H not empty. If lower G star lower H lower star G inverse belongs to H for all lower G in the group G, all lower H in the subgroup H, then H is a normal subgroup of G. Okay. This is a very useful criterion. If you're able to show that for any two elements, G and H, this expression belongs in H, you have proven that H is a normal subgroup of G. So let's write a proof sketch of this. Let's see why this is the case. Okay, so proof sketch. We're not providing a full proof, but we'll give the idea so that a complete proof can be written. Okay, so let G be an element of the group. So let G be an element of G. We aim to establish that the left and right cosets generated by this element are equal to each other. So we aim to establish G star upper H equals upper H star G. Our method is the following. We're going to pick an element of G star H, and we're going to demonstrate that it also is an element of H star G. So let's begin. And then, of course, the opposite will have to be established as well. Pick an element of H star G, show that it belongs to G star H. Once those two steps are completed, you have a proof of the statement. Okay, so let X, so let's pick a generic element of the left coset. So let X be an element of the left coset. If X belongs to the left coset, then we know that there is some value H in upper H, let's call it H1, such that X equals G times H1. So there exists an element H1 of upper H such that X equals to G star H1. Very simple. Let me put the identity. This is a slightly ingenious step. Let's put the identity there. Let's take this and start it with E. Now we know that this is true. G star H1 is the same as G star H1 star E. But E is the same as G inverse G. So this is the same as G star H1 star G inverse star G. That's just the identity. Where is this element? Where is this expression? This expression belongs to H because of the hypothesis. Our hypothesis says that G inverse belongs to H for all G and H. So this guy belongs to H. So we can call it H2. So let H2 equal to that expression, G star H1 star G inverse. So we conclude that X equals to H2 star G, which belongs to the right coset of H generated by G. Okay, so this is halfway. We're halfway done. The other halfway will be done quite similarly. So consequently, so we could say consequently, G star H is a subset of H star G. So similarly, you can establish that H star G is a subset of G star H, and at that point you will be complete with the proof. So let's write that final goal in move on to another item. So in a similar fashion, we can establish that the right coset H star G is a subset of G star H. Once you have these two are subsets of each other, that's when you get that they have to be equal. So therefore, H star G must equal to G star H, or you can write them in the reflexive fashion. Okay, one more item before the conclusion of this video is that when you have two groups, G star and G prime dot, and you have a homomorphism phi from G into G prime, then the kernel of G will be a normal subgroup of G. So we're going to mention the result in a separate installment. We will be doing the simple proof, but there. So let G star and G prime dot be groups, and let phi from G into G G prime the A group homomorphism. The kernel of P under the operation of G, so star, is a normal subgroup of G star. Okay, so we will write a proof of this in a separate installment. Basically, what you need to show is that all elements x such that phi of x is the identity in a G prime, left cosets and right cosets are identical. Okay, that concludes this particular installment.